Hello everyone, welcome to my channel. Here I am with another video, and in this video we are going to have a look to finite element method. I will solve Poisson equation using finite element method. Therefore, you can compare this video with the previous one. It was solution of Poisson equation using finite difference method. We will have a brief look to the strong form and weak form of a partial differential equation, and we will see how weak form of a PDE is combined with finite element method to provide us a numerical solution. If you are interested, stay with me. Okay, let's start. Imagine that we have Vx, that is a solution of some partial differential equation, but this solution is analytical solution, therefore we have the exact solution. We know that numerical solution indeed is an approximate from this analytical solution. And in this video, we want to show that this numerical solution can be expressed as the superposition of some function, psi, and this function is known as a base function or weight function or shape function. And we will see that if we can calculate this coefficient of this superposition, we can say that this numerical solution is a good approximation from this analytical solution. As you know, for a numerical calculation, we need first to discretize the domain. Imagine that this blue line that shows the Vx, that Vx is analytical solution, and we only are interested to calculate the numerical solution only at this nodes number 1, number 2, 3, 4, 5, 6. And the distance between, or let's say the domain, the space between each two nodes known as an element. Therefore we have 1, 2, 3, 4, 5 element and 6 node. And if we calculate indeed this coefficient at this node and just connect this node to each other, you can see that this dashed red line can represent with good approximation this analytical solution. And about the shape function or weight function, this shape function, as you see, it should have some characteristics, and the characteristics is following that this function should be 1 only at one grid, and at all other grid or nodes, the value of this shape function should be 0. As you see here, psi1 is 1 only at the position of node number 1, and at all other nodes, this psi1 is 0. And here we have the same situation for psi2. The value of psi2 here only at the grid number 2 is 1, and at all other nodes or grids it is 0, and the same for psi 3, 4, so on and so forth. Therefore, by assuming that we have 6 nodes and therefore we have 5 elements, this numerical solution should be a superposition of this psi 1, psi 2, 3, 4, 5, 6, and the coefficient of each shape function or weight function indeed clamp this function, this function to the exact solution. And if we can calculate this coefficient, therefore it will be our numerical solution. But we are not restricted to uniform mesh or uniform grid. We can use dense mesh when the gradient of the function is severe, as you see here, and we can have less number of mesh at the points where the gradient of function is not very big. Okay, this is the Poisson equation that we solved in previous video using finite difference method. I'm using the same notation, and I just assume that here this Poisson equation is normalized to epsilon, but you know that here we should have some epsilon, and I can write the left hand side like this. And as you know, epsilon should be somewhere here. But here I normalized this function to the epsilon, and I'm assuming that the domain of simulation is uniform. And this or let's say this shape of this differential equation is known as strong form of the equation. We are trying to first find the weak form of the such a let's say such a differential equation. If this equation holds, Yeah, it is possible to show that this might be also whole, and this equation should be satisfied. And this psi x indeed is our shape function. Now let's start with a very simple case. Let's assume that we have only 2 elements and 3 grids. Yeah, and as you see here, inside of each element there is 2 shape function. Yeah, psi 1 at the element 1, psi 2 at the element 1, and for the second element we have another psi 1 and another psi 2. Yeah, and you notice that here the position of the nodes for each element is known. For the element number 1, the left node is x1 e1 and the right node is x2 e1. And also for the second element, the left node is x1 e2 and the right node is x2 e2. And let's assume that the value of this unknown v that we are trying to find here at the node number 1 associated to the element 1 is v1 e1, and at the node number 2 associated to the second node is v2 e1. Also the value of this function at the second element and the node 1 is v1 e2, and at the second element and the node 2 it is v2 e2. Now I want to integrate this equation, integrate both hands side of this equation over this element. Yeah. Okay, it means that here I need to integrate from x1 to x2 this, and again right hand side I want to integrate from x1 to x2 this function dx. Yeah, and if you notice, you can see that we have a dx here and we have a dx here, therefore this can cancels each other, and after that we have this equation, the same equation. Yeah, and we can simplify this equation indeed using by integration by part. Yeah, and you know that the integration by part formula is following. When we have an integral of u dv, it can be written as uv minus integral v du. And you notice that here in the psi x is our u, and e of this function, that is dv over dv over dx is dv. Yeah, therefore if I just applied integration by part to the left hand side of this equation, I have this for the left hand side. Yeah, and the right hand side is the same, and I did nothing. I want to okay, and just to make it a bit simple, I just multiply this part with dx, and also I divide this function with another dx. Therefore, we have two multiplication of two derivative, dv over dx times 2 d psi over dx. Yeah, I want to define some new function e that is minus dv over dx. From physics, we know that this d indeed is displacement vector. If v is potential, we know that the multiplication of the relative permittivity times, or let's say permittivity times to the electric field, will be the displacement vector. And because here I assume that the epsilon is 1, I normalized this function to the epsilon, therefore displacement vector simply will be this. And if I substitute limits of the integral here for this part, what I have will be psi x2 e1, yeah, times 2d that we defined here at the position of x2 plus psi x1 times 2d at the position of x1. Okay. I did nothing. I have again this equation. We have the same equation. I just send this part from left hand side of the equation to the right hand side of the equation. In this case, I have this equation. Nothing is complicated. We just multiplied Poisson equation to some function, yeah, and we used integration by part, and we defined some new function d, and we did some substitution, and we achieved to this equation. But we need to notice that here we indeed is the numerical solution, and we say that this numerical solution can be superposition of some function, and because we are doing integration over only one element, yeah, therefore inside this element we have two shape functions, psi1 and psi2, and I just neglected here superscript e1, and also here that shows this shape function are related to the element number 1. Yeah. Therefore, I just substitute this definition in this equation. Yeah. I did nothing complicated. I just put this Vn here. Therefore, we have d over dx of this function times to the rest is the same. Yeah. But again, I'm recalling this geometry, and we see that inside this element number 1, we have psi1 E1 and psi2 E1. Therefore, we need to write this equation for both shape functions psi1 and psi2. Therefore, one time I just substitute psi1 here, 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 and here. Yeah, and another time it will be psi2 here, 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 and here. But we remember that psi1, you can easily see that psi1 at the position of the node x1, it is the value of psi1 is 1, and at the second node this is 0, and vice versa condition is hold for psi2, means that value of the psi2 at the position of x1 e1 x2 e1 is 1, and the value of this function at this position is 0. Therefore, we just substitute here 1, it should be 0, psi1 at the right node is 0, psi1 at the left node is 1, psi2 at the right node is 1, and psi2 at the left node is 0. And if we do this substitution, we will simply get to this system of equation that we derived. Let's move further. And what we want, I just here I just used I expanded this sigma function, and we have v1 e1 times 2 psi1 e1 plus v2 e1 times 2 psi2 times 2 psi2x. Yeah, I just expanded this sigma function. And let's make it a bit simple. We know that this v1, v2, and also v1 and v2 here should be constant. Yeah, these are some coefficient, and this coefficient is constant. Therefore, it can be come out of this derivative and out of this integral. Also, this v2 comes out of derivative and out of the integral. Therefore, I multiply this to this term, and I will have this term. Yeah, v1 is coefficient that came out of derivative and integral, and here we have only d psi1 over dx here, and d psi1 over dx here, and we have another dx here, and v1 came out, and the second term v2 here came out. What we have is d psi2 over dx, that is written here, and times 2 d psi1 over dx. Yeah, and the same for the second, just a bit simplification. Make it a bit simple in terms of notation. Let's define this integral with some new, let's say, new function k, and we can see that we can call this coefficient, let's say call this integral with k11, and let's call this one with k12. This one can be k21, and this can be k22, and here let's define this integral with s1 and s2. For using new notation, this is the system of equations that we derived, yeah, simply, and we can easily write this system of equation in a matrix form. And you know that in a matrix form, simply it can be written like a 2 by 2 matrix times 2 by 1 matrix equal to some matrix that is 2 by 1, and also this one is 2 by 1. And what is kij, elements of this matrix? This is minus integral from the lower, let's say, nodes of the element 1 up to the upper nodes of the element 1 times 2 d psi I over dx times 2 d psi j over dx times 2 dx. Yeah, and okay, and the s here, si, should be integration again from x1 up to x2 psi I times 2 f times 2 dx. And what we did such a matrix form of the system of equations for the element number 1. In the same case, you can easily show that such a system of equation in a matrix form should hold for the element number 2. And we can derive for infinite number of elements, or for desired number of elements, we can derive such a 2 by 2 system of equations for each element. Yeah. Now, okay, again, we have the system of equations that we derived, and this is definition of K, this is definition of S, and I'm recalling that, okay, now it's better to calculate this, the coefficient of this matrix. But before that, let's make another simplification. If we assume that there is some element at any desired location inside the simulation domain, it has some lower boundary x1 and the upper boundary of the x2, and there is two shape function of psi1 and psi2 as here, that is, this function here is 0, here is 1, and this function here is 0, and here is 1. But it is convenient to define some, let's say, some normalized coordinate to get rid of the position of x1 and x2, because these elements can locate it at any place, yeah? And if we want to just get rid of the location of the, let's say, lower boundary of element and upper boundary of element, we can define some normalized, let's say, normalized vector, yeah? And this normalized vector, if we define following, that is 2 times 2 x minus x1 divided by x2 minus x1 minus 1, and we can see that if we substitute x1 in this new coordinate, zeta will be 1, because x1 minus x1 will be 0. This term is 0. What is left will be minus 1. And if we substitute x2 here, what we get is 2 times 2 x2 minus x1 divided by x2 minus x1. This cancels each other, and zeta takes the value of plus 1. Which means that in new coordinate, when the position of the nodes is x1, the value of zeta should be minus 1. And when the position of nodes is x2, the value of zeta will be plus 1. What about psi1 and psi2 in new coordinate? You can easily check them. Psi1 zeta can be like 1 minus zeta over 2. And you can simply check it when zeta is minus 1. If we put minus 1 here, it will be 1 plus 1 over 2 will be 2 over 2, and this will be 1. Therefore, here you can see that psi1 is 1. And when zeta is plus 1, psi1 is 0. If we put plus 1 here, 1 minus 1 will be 0. Therefore, psi1 will be 0. And we have the same for the psi2. Therefore, in new definition, let's say in normalized coordinate, the definition of zeta is like this, and it's connected to x using this formula. And the function of, let's say, the linear shape function that we defined in new coordinate should be like this: 1 minus zeta over 2 and 1 plus zeta over 2 for the second shape function. Now, okay, we have the shape function, and this is the definition of zeta that connects x to, that is connected to the x. Now let's derive this matrix based on zeta. Therefore, we need to substitute dx here, and before that, I just defined this x2 minus x1 with h. This x2 minus x1 is nothing but just delta x between the node number 1 and node number 2 for any desired element, And we can, instead of this function, psi I over dx, we can simply write d psi I over d zeta times 2 d zeta over dx, And from this, we can see that d zeta over dx should be nothing but just 2 over h, And again, from this function, we can simply show that dx should be h over 2, times 2 d zeta. Therefore, I substitute dx here, d psi I over dx here, and d psi j over dx should be similar function. After substitution, what we have, you see that we have a h over 2 here, and we have 2 over h here that cancels each other, what is survived is just a 2 over h. And this is constant, and 2 over h comes out of the integral, and you know that the limits of integral in new coordinate of zeta should changes from minus 1 up to plus 1 when x changes from x1 to the x2, simply. Therefore, let's try to calculate this coefficient of this 2 by 2 matrix. And the first coefficient is k11. It means that we have minus 2 over h, integral from minus 1 to plus 1, d psi 1 over d zeta times 2 d psi 1 over d zeta times 2 d zeta. And what is d psi 1 over d zeta? This is nothing but minus 1 over 2. Therefore, we have minus 1 over 2 here, minus 1 over 2 here. After simplification, 2 cancels this 2, and what is left is 1 over 2 he, integral from minus 1 up to plus 1 of d zeta. And we know this integral is simply zeta. And if we put the limits and calculate it, finally we will get this for the k11, as you see here simply. Let's try to calculate another coefficient, k21. For the k21, what we have, it is minus 2 over he, the same integral, d psi 2 over d zeta times 2 d psi 1 over d zeta. And again, if we put psi 2 over d zeta, that is 1 over 2, d psi 1 over 2 d zeta, that is minus 1 over 2 times 2 d zeta, yeah, after calculating out this integral of d zeta, that is zeta, and if we put the limits of integral, we will get 1 over he. For the other coefficient, k12, you can simply show that this is 1 over he again, and for k22, it is minus 1 over he. Yeah, okay. And, simple system of equations, we calculated this coefficient matrix that is a function of delta x, or function of h. And this h is nothing, just distance between two nodes. Let's try to calculate S1 and S2 also, and we know that we defined Si to be like this, yeah. But in new coordinate, it should be like following that d psi. Yes, we should indeed put d psi zeta instead of psi x, and that's nothing but 1 minus zeta over 2, and f is the same function, and we calculated that dx is connected to d zeta like h over 2 d zeta. And if you calculate this integral simply as you see here, finally you will get, this will be 2, and finally you will find s1, that is h over 2 times to the f. Yeah, and here we assume that the f is function and comes out of the integral. And if you calculate s2, also just by substitution of this function here, that will give us the s2. It will be again h over 2 times to the f. Okay, what we did, we assume that we have two elements, we have 3 grids, and we calculated this system of equation in a matrix form for the element number 1, and simply the element number 2 should have the same system of equation. And what is changed here, just here he1 that is associated for the element 1 should be replaced with he2, and here we have at the element 1 we have potential here, and at the element 2 we have potential v1 at the element 2 and v2 at the element of 2 here, and nothing is complicated. But let's try to combine these two matrices. But before that, I'm defining this v1 at the position of the element 1 with v1, and we see that this v2 at the second element and the v1 at the second element, yeah, v2 at the first element and v1 at the second element should be the same, and I define it with v2, and here I define this with v3. And if I want to combine this element, okay, what I need is that I need to add I have v1 here, v2 here, I need to add v3 here, yeah. But also I need to add some row and some column to this matrix, and if you calculate this multiplication times to this, everything will be 0. Therefore this system of equation is exactly the same. Yeah, I just added some 0 column and 0 column and 0 row to this matrix, and also for the second one I need to add a 0 row here and a 0 column here, and if you multiply this row to this column, everything will be 0, and this system of equation indeed is the same. Yeah, now I can combine these two system of equations to each other. Yeah, simply you can see that this element will add it to the this, and we have here this will add it to the this, we have it here, this is added to this, and it gives 0. And here we have the same, except in this central element that here we have minus 1 over he1 and we have minus 1 over he2. Therefore we have minus 1 over he1 plus 1 over he2, and the rest is the same. This are added to this 0, therefore it gives us the same, and here we have the same matrix, and here only central element will add to each other, and here this d2 will add it to this minus d1. But from physics, we know that, okay, we mentioned that this D is what? It is displacement vector. We know that it at any, let's say at any boundary, that there is no surface charge, the displacement vector at the left-hand side of the boundary and the right-hand side of the boundary should be the same. And we know it from the physics. Therefore, this D2, that is indeed the displacement vector at the node number 2 associated for the element number 1, and this D1 is displacement vector at the node number 1 associated to the element number 2. Yeah, it should be 0 simply. Therefore, we have again the same matrix by considering that the central element here is 0. Yeah. And we derived this matrix form of the system of equation only for 2 elements. Yeah. If we repeat it for the large number of elements, like what I did for the 5 element, you can easily show that this matrix will be like this. And what is changed here, you can imagine that this central part can be expanded. We have here, okay, when we have 2 elements, we have summation of the inverse of delta x for element 1 and 2 here. It will be summation of the inverse of the, let's say, delta x for the element of 2 and 3, here 3 and 4, 4 and 5, and finally at the last element we have only 1 over HE5. Here our last element is 5 and here last element is E2. You can simply show it, and here when we have 5 elements, the number of nodes is 6. We have the same here, and this one will be like this, and we have the same matrix that central element is 0, because when we connect the elements, neighboring elements to each other, displacement vector will cancels each other. Therefore, this all of this element should be 0. Yeah. But we have not still applied boundary condition. Yeah. What about boundary condition? We know that if we want to have some solution for Poisson equation, we need some finite solution. Yeah. Without boundary condition, we have infinite number of solutions. But boundary conditions limit the solution to some, let's say, to only unique solution. Therefore, we know the value of the psi1, value of the potential at the first node, that is left boundary, and at the last node, that is the right boundary. How do we can apply boundary conditions? You can just write the system of equation not in a matrix form, just multiply this to this, this to this, and write a system of equation. And we know that when we know the boundary value of the boundary condition, we need to send this known value to the right hand side of the system of equation. Yeah. But the second thing is that without writing of boundary conditions, yeah, I mean without writing of system of equation in non-matrix form, you can easily see that we need to have the multiplication of this term to this term and multiplication of this term to this term, and we send this multiplication and this multiplication to the right hand side of the equation, and after that we need to fit this first row at the left of the equation, let's say left hand side of the equation, and the first row at the right hand side of the equation. Also we need to delete last row here, yeah, last row here and last row here. We need, therefore when we do it, we have only 0 matrix that we do not need anymore. Also we need to delete this and delete this column, and what will left will be this central, yeah, this central matrix and this central element here and central element here. I just recall you that this slide is from previous video. In a finite difference method, you remember that because we know the value of the potential here and here, and when we calculated the definition of this Poisson equation using finite difference method, we achieved such an equation. And when we derive the system of equations by considering that the number of nodes is 6, we derived 1, 2, 3, 4. We derived 4 system of equations when the number of grids is 6. Yeah, then you see that here V1 indeed is our known potential at the left boundary, and V6 is our known potential at the right boundary, and we send this and this to the right hand side of the equation, and finally we ended up with some 4x4 matrix. Again, we have the same. When the number of nodes is 6, yeah, and the number of elements is 5, we also have only 4 system of equations, and the matrix form of this 4 system of equations, considering that this boundary conditions should comes to the right hand side here, will be following. Very simple. We just use some trick without extra calculation, and the trick is that, okay, if we want to consider boundary condition in the second equation, yeah, or in the second row, we need to send multiplication of this term and this term to the right hand side, and in the 1, 2, 3, 4, 5, in the 5th row, we need to send multiplication of this term to the right hand side. Therefore, in this, using this trick, we are considered boundary condition simply, and this is indeed the matrix that comes from the left hand side to the right hand side, and this matrix indeed is due to the boundary conditions. Now what we have a matrix that is known because it only depends on the h, and h is delta x between each nodes. Yeah, and let's define this matrix with M. We have V that are interested for calculation of this V. We have a right hand side matrix. Yeah, again this matrix is known because we assume that we know the F and we know the H. Okay, and this, let's define this matrix with right hand side B. This B stands for boundary conditions. This matrix comes from applying of the boundary conditions. We have a matrix multiplication of M times 2V should be equal to the sum right hand side matrix, and all we need for calculation of V is that we calculate the inverse of this matrix and multiply this matrix to the right hand side matrix, and we know that we are interested for calculation of the Poisson equation from 0 up to D, and at the D we know the value of the potential, and here HE, HE1, E2, E3, E4 and E5 are the delta X of the neighboring, let's say, node. Yeah, that's it for the theory part. Let's try to implement what we derived here. Yeah, let's try to implement this calculation in MATLAB. Okay, if you remember, this is the same code that we wrote for the Poisson equation using finite difference method, and we had a brief discussion about analytical solution, and we compared the numerical solution with analytical discussion. Therefore, I just copy the same commands that we wrote in previous video, yeah, here, just for analytical solution, and I paste here. Okay, I assume that the number of nodes here is 50, and the thickness of the simulation is from 0 to up to D. That D is 12 micron. F is some constant, 1E10. The left boundary conditions is -half, and the right boundary conditions is -0.6. And here we assume that, okay, x changes from 0 to D with the number of n. And here h should be d over n minus 1. But now, because we want to save all h or all delta x, therefore I just delete this one, and I want to use different number for plotting of the let's say numerical solution or analytical solution. If I press F5, okay, I'm just save it somewhere here, FEM2, Poisson FEM2. Okay, and this is indeed the analytical solution that we discussed in previous video. Now we want to have numerical solution using FEM. Yeah. Now let me copy these commands from here, Ctrl C, and paste it here and change it to XA, and number of let's say the number of points that we are plotting analytical solution, that be 100. Okay, this is 100, therefore it is analytical x, and this is analytical x, and this is analytical x. Yeah, F5. Okay, this is analytical solution. And for numerical solution, number of nodes here is defined with, let's say, 50. But what about h? We need to save all delta x to some let's say, variable. I define it with h, and the size of h should be changed from 1 up to n minus 1. Yeah, and I say that, okay, save x 2 up to n minus x from 1 up to n minus 1 to the h. And this is our delta x as you see here, but because we are using uniform delta x, every h is the same, but if we have non-uniform x, therefore h or delta x should be different. Okay, what we need to define matrix M, and the size of matrix M, zeros, should be what? N minus 2 by n minus 2, because when number of nodes is 6, okay, let's start with a small number. When number of nodes is 6, number of elements is 5, the matrix should be 4 by 4, therefore n is 6, therefore size of this matrix should be 4 by 4. And what else? Okay, we say that, okay, I want to define this matrix. I define some loop for I changes from 1 up to n minus 1, and okay, let it be 2. I want to change this matrix from 2, okay, from 2 up to n minus 1, and mii, it means that, for example, m22, here m22 is minus 1 over h2 plus 1 over h3. It means that it should be minus 1 divided by, okay, hi, that is h2, plus hi plus 1, I plus 1, that is h3, okay? What about this m21? Okay, m21, here should be m2. When I is 2, it should be I minus 1. Yeah, it gives us m2, 1. It means that second row and first column, therefore it should be m21. This one, m21. This one is 1 over h e2. It means that it should be 1 over h I, yes. And about m12, it means that it should be m I minus 1, and I. When I is 2, it gives us 1, 2. First row, second column. This is also like previous again. It should be 1 over hi. Therefore, I copy it from here and paste it here. But one thing is left, and that is nothing but when for m11. M11 also should be, okay, I'm defining it with mi. But before that I define that I when I is 1, it should be again the same. Control C here and Control V. It says that M11 is minus 1 over H1 plus H2. This one. 1 over H1 plus, I made a mistake here. It should be separate, 1 over H1, yeah. Here minus 1 over H2. Also here it should be 1 over Hi minus 1 over Hi plus 1. Now this is correct. 1 over Hi minus 1 over Hi plus 1. I define this, okay. Then we define matrix M. The size of matrix V will be defined by the size of M and right hand side. Therefore, I need to define right hand side matrix. Therefore, the size of right hand side matrix, here. Okay, I say that, okay, right hand side. The right hand side should be zeros, but n minus 2, 1, yes. And what is right hand side? Right hand side matrix. Again, we need to define some loop. Therefore, I say that, okay, for I from 1 up to n minus 1, yes. n, okay, and the right hand side 1, right hand side I, control X, control V. Okay, the first right hand side should be what? It is nothing but f over 2 h1 plus h2. It means that it should be half times f times what? hi plus hi plus 1. And it creates right hand side matrix for us. We need another right hand side B. The size of right hand side B should be the same. Therefore I define it right hand side B, the size should be the same. And what is right hand side B? Right hand side B is 0 except in the first and the end. And the first one is what? Okay, I say that the first right hand side B, or the right hand side B1, is nothing but minus V1, that is indeed V left, left boundary condition, it should be V left divided by H1, yes, divided by H1, and the last one is minus V6 divided by HE6, therefore I'm just copying it, Control C, Control V, and the last, let's say, row should be V right divided by last end, that is HN. Okay, and what else? And we say that, okay, V should be what? V should be M backslash right hand side. M should be Control C, right hand side plus Control V, right hand side B. But we notice that this V only contains, let me change this V to V numerical C. It means that this is numerical solution only at central grid, because we have V2, V3, V4, and V5. And finally, the numerical solution, that is Vn, should be, I'm allocating some memory to this matrix. It should be 0, n and 1, yeah, n and 1, and we know that Vn, first one in numerical solution, that is left boundary, this is V left, Control C, Control V, and V numerical n is right hand side boundary, and that is V right, and inside, using such a loop, for I changes from 1, let's say, up to n minus 1, and I say that, okay, give this Vn central of I to the Vn of I, okay, Vni plus 1, yeah. Okay, we have the Vn1, that is V left, we have the Vn end, but we want to give this central V2, V3, V4 to this matrix. Therefore, when I is 1, yeah, when I is 1, it gives the first row of this matrix to the second row of this matrix. And when I is n minus 1, it will be Vn, therefore this one should be n minus 2. When I is n minus 2, it gives the last VNC, because the size of this VNC should be n minus 2. The last VNC to the Vn minus 1, that is one before last in this array. And finally, that we have Vn, I want to plot this, let's say, Control C, I'm plotting X and Vn, yeah, and let's plot it with some cyan color and with marker of O. Let's check everything is true. Here is X and we have X here, yeah. Here we saved H delta X to the H, and here we calculated. Okay, let's just press F5 and check if there is any error or no. F5. Zeros is not known, and this is M. Here it should be zeros. Zeros, press F5 again. And here index should not exceed from, here it should be -2. And another error, it says that, and also here it should be up to n-2. Another error, we have the matrix dimension must agree. Why it is not agree? Okay, let me check CLC. Here right hand side size is this, right hand side is this. I want to control size of matrix M. Oh, I mean size. Yes. No. CLC. I say that, okay. Size of M. What is size of M? 4 by 4. It's true. What about size of right hand side? Right hand side. Size is 4 by 1. This is again true. And what about right hand side B? It is again 4 by 1. So why does it gives error? Backslash. This should be not slash, it should be backslash. Okay. And now it works. You see, this indeed is cyan color. Okay, let me define legend. And the first one is analytical. I show it with A, and the second one is, let's say, numerical finite element method, and this is analytical. Yes, legend. Okay, this one cyan is analytical, and this magenta is analytical, and this cyan color with circle marker is numerical using finite element method. And when I increase here, you see the number of nodes 1, 2, 3, 4, 5, 6. And yeah, the number of element 1, 2, 3, 4, 5. And if I increase the number of nodes or elements, let it be, for example, 100, you see that they have exactly the same analytical and, let's say, numerical solution. And a few words about the advantage of the finite element method over to the finite difference method. First of all, you can use any element, any shape for the element. Therefore, when you are dealing with some non-rectangular geometry, the finite element is better to be used. And the second thing is that in a finite element, we are using, let's say, weak form of the PDE. In the what is weak form of the PDE? Weak form of the PDE indeed is integral, yeah, rather than the derivative. We derive it here. Yeah, this is indeed the weak form of the Poisson equation. Yeah, and in the weak form, you see we are dealing with some integral rather than the strong form. This is the strong form of the PDE. That in strong form we use derivative, but in weak form we use integral. Therefore, for example, when we have a function that is not continuous, yeah, imagine that we have some function that is not continuous. For example, what we have in material properties. Imagine that we are trying to, let's say, solve Poisson equation in this domain, in one-dimensional domain, yeah, x. But here we have different epsilon. For example, we have epsilon 1 here, and we have epsilon 2 here. Okay, and we know that in Poisson equation, here we should have some epsilon in it. Here multiplies to the dv over dx. Therefore, if we have different epsilon, it means that where is it? Okay, if we have different epsilon, it means that, let me change the pen color to the blue, it means that, for example, epsilon at this domain is some value. For example, imagine that this is, for example, relative permittivity. Imagine that relative permittivity here is 1 and relative permittivity here is 3. Therefore, this epsilon is discontinuous, and it will be challenging to calculate the derivative of epsilon because we have over dx of epsilon dv over dx. It means that we need to calculate the derivative of epsilon with respect to the dx. But when this function epsilon is discontinuous, yeah, it's a step function, here we cannot calculate the derivative. On the other side, if we keep that epsilon here, the epsilon should be somewhere here. But here we can easily calculate the integral of the epsilon from here to here, then from here to here. Therefore, that's why weak form of the PDE helps us to deal when we have, for example, discrete material properties. I think that's it. If you like the video, do not forget to like it, subscribe to the channel, and if you have any question, you can ask in the comments. See you.